Welcome back, and in this next video we're going to be looking at the structure of covalently bonded substances. So they all have covalent bonding, but their structure is quite different, and you need to understand the difference between a giant covalent lattice and a simple molecular structure. Okay, so we're on page 8 of your notes and we're looking at these two types of structures, simple molecular and giant covalent lattice structures. So first of all, molecular lattices. These are lattices which are held together by weak intermolecular forces. For example, iodine here. Iodine is a diatomic molecule, I2. In the solid state, it's held together by these weak intermolecular forces between the molecules. Now, because iodine is quite a large molecule with a large number of electrons, the actual intermolecular forces are stronger than normal. So when the iodine melts, we're only overcoming the weak intermolecular forces between the molecules and not the strong covalent bonds in the molecules. It's important that you know the difference between those two things. So as the molecules gain kinetic energy, they eventually are able to overcome these weak intermolecular forces and turn from a solid, in this case, directly into a gas, because iodine sublimes. Ice is another good example of a molecular solid. Again, you've got strong covalent bonds within the molecule, but weak intermolecular forces between the molecules. And it's these weak intermolecular forces which are broken when the solid melts, not the strong covalent bonds in the water molecules. And we'll study that in a later topic. Moving on to giant covalent lattices. These are all covalently bonded structures, but they have a giant covalent lattice. Many of them will be familiar to you from GCSE level. So we're going to look at diamond. Diamond is an allotrope of carbon. Allotropes are where the element has it's the same element, but it's arranged in different ways. And we're going to have a look at diamond, which is a giant covalently bonded structure. It has a very high melting and boiling point because in this case I have to overcome strong covalent bonds within the structure, not weak intermolecular forces between the molecules. There are no molecules of diamond. So there's my structure of diamond. I've got one carbon atom covalently bonded to 4 others. And those covalent bonds are very short and very strong, and that's why diamond has a very high melting point, because you've got to overcome those very strong covalent bonds throughout the structure in order to get it to melt. In fact, there's very little difference between the melting and the boiling point, because once you've overcome these strong forces of attraction, it takes very little to turn it from a liquid into a gas. Physical properties are all related to that structure. They're hard, high melting point, there's no delocalized electrons or mobile ions, so it doesn't conduct electricity, and it's completely insoluble in both polar and non-polar solvents. So when we compare it with iodine, you can see they've got very different properties. Iodine, that grey solid with covalent bonds between the atoms, but weak intermolecular forces between the molecules. And that explains why it has such a low melting and boiling point, whereas diamond has the highest melting point of any element on the periodic table. In diamond, we need to break the many strong covalent bonds, where in iodine, you're only overcoming the weak intermolecular forces between the molecules. Notice again, you're not splitting up the iodine molecule. You're only overcoming the weak intermolecular forces. Moving on to silicon, silica or silicon dioxide. They all have this tetrahedral arrangement of atoms, and that means they have very similar physical properties. They all have high melting points, they're all hard, and they all do not conduct electricity. You could also add in there that they're all not soluble in water or organic solvents. Silicon is a group 4 element. It has a lower melting point than diamond because of the larger radii of the atoms. Therefore, the covalent bonds are longer, and we know that longer bonds are weaker bonds. Silicon dioxide, or otherwise known as sand, is again this giant tetrahedral arrangement, and there it is. So that's very similar structure to diamond, except now we have these little red blobs representing my oxygen in between my silicon atoms. But you can see it's got a very similar structure to diamond. And again, very similar physical properties. Doesn't conduct electricity, it's insoluble, hard, and of the high melting point. So moving on to the next allotrope of carbon, and that is graphite. And graphite has layers of carbon atoms which are covalently bonded and weak intermolecular forces between the layers. So it has a very different structure from diamond, although the bonding is identical. It's carbon-carbon covalent bonds. But there you've got the weak forces between the layers of carbon atoms. So each carbon atom is bonded to 3 others. Each of these bonds is the same covalent bond that there is in diamond, but this means that you've got 1 electron free. We call it a delocalized electron, because only 3 of the outer shell electrons are involved in bonding. So you have these strong covalent bonds between the atoms, just as you do in diamond, but here you have this weak, there we go, so weak intermolecular, or IMF forces. We call them London forces, and you'll study those later on in the year when we study intermolecular forces in detail. You have these delocalized electrons which can now flow in this layer. And this helps to explain why graphite can both conduct electricity and heat, because these electrons are free to move along a layer. They can't move between the layers, but usually there's enough of a path that they can sort of form a wiggly line through. They also conduct heat very well because the electrons collide with each other and transfer kinetic energy throughout the structure. Technically, graphite only conducts along the sheets because they can't conduct across the layers. However, they have also good lubricants or useful in pencils, because those weak London forces allow the layers to slip, leaving behind a layer. And that layer is known as graphene. It's a single layer of graphite. This was what won the Nobel Prize in 2010 for physics, which was this discovery. Graphene has some very unusual properties. It's transparent, flexible, and conducts electricity. It's different from C60. C60, otherwise known as Buckminster fullerene, is considered a molecule. The reason for this is it has a fixed number of atoms in the molecule. It doesn't have C61 or C659, it is C60. Whereas graphite, as well as graphene and diamond, there's a variable number of atoms. So when we give the formula, it's similar to the formulas we give in ionic bonding. There we've got diamonds and graphite side by side. They both contain strong covalent bonds, but because of their structure, they have very different properties. Diamond is not able to conduct electricity because all the electrons are localized within those covalent bonds, whereas graphite is able to conduct electricity because it only uses 3 of its outer shell electrons, with the 4th being delocalized. Diamond has a much higher density because you can pack the carbon atoms quite closely together. You get a large number of atoms per unit volume. Whereas in graphite, you've got large spaces between the layers, and that reduces the density. Both of them are insoluble in solvents, both polar solvents like water and non-polar solvents like cyclohexane. Last but not least, I'm going to compare a simple covalent structure like carbon dioxide with a giant atomic lattice like silicon dioxide. So again, my simple covalent structure cannot conduct electricity, neither can my giants, both because all the electrons are localized to the bonds. Giants are insoluble in both water and organic solvents. Simple covalent structures like carbon dioxide, they tend to be very soluble in organic solvents. In this case, the carbon dioxide is able to react with the water and form this hydrogen ion and hydrogen carbonate ion. So it will dissolve in water due primarily to the reaction with the water. The giant covalent lattice has very high melting and boiling points because you need a lot of energy to overcome those strong covalent bonds, whereas simple covalent requires very little energy to overcome the weak attractions between the molecules. Notice again, we're not breaking the strong covalent bonds in the carbon dioxide.